Welcome everyone. In this video we will prove two of the four kinematics equations using calculus. Now, I am going to prove only the two of them in this video, and specifically the one for velocity and the one for displacement. In the next video, using those two equations, we will prove the other two. And in the next video, we won't need to use calculus, so that's why I divide this proof into two parts. In this video, we use calculus, and in the next video, we just use algebraic manipulation. So let's get started. Now, kinematics is the study of motion. It isn't interested in how the motion is caused. To investigate that, you would need to use dynamics, which is the study of force. So kinematics says that the acceleration is the derivative of velocity with respect to time. Alright, this should make sense because at the end, acceleration is simply the rate of change of velocity. Well, this is what it's saying, this definition. So, in this definition, if we multiply both sides with dt, and I know it is just a notation, I mean, how can we think of it as a factor? But let's keep it simple and do that. So, this is saying that we have a times dt will give us a small dv. So if we take the integral now, for the left side integral, I'm going to start from t is equal to 0 and go to an arbitrary t, any t. And now on the right side, I will start with our velocity value at time is equal to 0. Well, this is our initial velocity, which I will call v0, and for the upper bound we will have vt, the velocity value at an time equal t. At any time, this is a general v, and this is a general v, and this is the initial v. So this is, and here we need to make a very important statement. We need to say that the acceleration is constant. This is incredibly important. For the four kinematics equations that we are going to discuss in the next two videos, this video and the next video, they work if and only if the acceleration is constant. They do not work under any other circumstance. The acceleration must be constant. This means that both the magnitude of the acceleration is constant and the direction of the acceleration is constant. Otherwise, you cannot use the four kinematics equations. So, if the acceleration is constant, this means that it doesn't change with time. So, we can take it out of the integral sign because constants can be taken out of the integral sign, just like you could take a constant out of a sigma notation. You can think of it just as a factor. So, we take it out of the integral. We have t is equal to 0 to t dt, and this is equal to, well, let's just solve the integral that we have on the right. What will this integral give us? The integral of dv will simply give us v, and we will substitute our upper bounds like this, vt, v0. Of course, using the fundamental theorem of analysis, something like that its name is, we will get this. Of course, I forgot this, but these are all vectors, of course. So, like this. Now, for this part, the second integral on the left, this will give us t like this, and we do t minus 0, we simply get t. So, as a result, we have the acceleration times time is equal to the velocity at time t minus v0, the initial velocity. So, we get a formula for our velocity at any time, which is simply v0, the initial velocity, plus the acceleration times time. So, this is the first kinematics equation, and we proved it. And notice here, this term, a times t, this is simply delta v. So it makes sense to get the velocity value at any time. You simply get the starting velocity, and then you add the change that we have, right? Initial velocity times the change in velocity should give you your final velocity. So since we got this out of the way, now let's move on to our second proof, which is finding a formula for displacement and position. They are very connected with each other, as we will see. So to do that, we use another definition that kinematics gives us, and that is the velocity is the time derivative of position. Now, if we multiply with dt just like we did on the last page, remember this step, if we do that, we will get v dt is equal to dx. Now, we will again take an integral. Surprise, surprise. We take the integral of both sides, and again, we're going to start from t is equal to 0. We're going to go to t. We now start from an initial x value, which we will call x naught, the initial position, and we go to some position that we have at time is equal to t. Here we can again take the velocity out, right? Nope, we can't. Notice here, we took the acceleration out of the integral sign on our last proof because acceleration was a constant. Is velocity is a constant? I mean, of course it isn't. We just found a formula for it. It is right here. We found that velocity changes with time. We have a time here, right? There's a t, so we cannot take it out of the integral. We need to integrate. But it won't be very hard, as you will see in a couple of minutes. So we substitute for the formula that we found for velocity, which is as follows. Maybe I should do it in red, just to introduce some color. Plus at. Again, we just proved this, right? It is right here. We just proved it. So we have our dt again. And I'm not going to write it in red anymore. We have dt, we have our integral from t is equal to 0 to time t. And this is equal to, well, let's just solve this integral again. What is the integral of dx? It is going to give us x. We have our upper and lower bounds, xt, x naught. Of course, these are all vectors. I keep forgetting, sorry about that. So in the end, we get xt minus x naught. And realize that this is just the change in x. So this is delta x, right? You have your final position minus your initial position. You get your change in position, your displacement. Now, what is the integral on the left? To do that, I am going to distribute this dt like this, and then I am going to break this integral into two integrals so that we will be able to deal with them. Now, the first integral is v naught dt, starting from t is equal to 0 to t. Then we have the other integral, which is, again, starting from t is equal to 0, going up to t. And this time we have I just realized a big mistake I made. I'm going to correct it. Here I put an arrow on top of t. That is, of course, not correct. I am sorry about that. Let me get rid of that. Wow, that's some mistake, right? So, oops. The acceleration is a vector, not time. Time is not a vector. So we put an arrow here as well on top of t, on top of a. I am really sorry for making that mistake again. And we have what we found just a minute ago on the right. Now, the first integral, you might be asking, is v naught a constant here? And of course it is. V naught is just your initial velocity. It might be 5 meters per second, if it might be 300 meters per second, it might be 3 times 10 to the power of 8 meters per second. If you are light, it can be anything, but it is just a number. It is a constant. So you have v naught like this. And you just have the integral of dt. You get t, your upper bound is t, lower bound is 0, t minus 0, you get t. You get the idea. Plus, now, in the second integral, is a constant? And it sure is, just we said it here, we just said that. It doesn't need to be a constant, but for us to be able to use the four kinematics equations, which make the questions a lot simpler, we assume that acceleration is constant. So we take the acceleration out. Now we have the integral of d dt. And I'm going to write it here. If you have the integral of x dx, this will be, and I didn't make a proof about this, but I will make a proof about this hopefully in a future video. You simply increase the power of x. So you get x squared and you divide by 2. Of course, you have your bounds here. Maybe you call it AB. So we do the same thing again here. We just have, instead of x, we have t. So we say t squared divided by 2. Now our bounds are, our upper and lower bounds are t and 0. But notice that if we substitute t for t squared divided by 2, we get t squared divided by 2. And if we substitute 0, we get 0. So t squared minus 2 minus 0, t squared divided by 2 minus 0, will give us t squared divided by 2. So we don't even need to write the bounds. This is what we get. And this is equal to x of t minus x naught, like this. And here, as I said, this is delta x. So we actually found a formula for displacement as well, which I want to state on a new page. Actually, I want to state all the formulas that we found on a new page. So we found one for velocity at any time, which says you have v naught plus the acceleration times time. Then you have one for the displacement, which is saying delta x is equal to v naught t plus 1 over 2 a t squared. And we also found one for position. We didn't found one, but if on this step here, if you add x naught to both sides, you get a formula for xt, which I'm going to do. So for xt, if you remember that delta x is like this, if you remember this, if you add x naught to both sides, you get a formula for xt as follows. You get x naught plus v naught t plus 1 over t a t squared. Here, this is just delta x, and here, this is just delta v. So all these formulas are telling us that you have initial value, you add the change to it to get the final value. And we found formulas for the changes in this video, assuming, this is incredibly important, that the acceleration is constant. Anyways, this is it for this video. As I said, in the next video, we will use these equations to prove the other kinematics equations. There are 2 left, and they are very important. And if you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.